Welcome to the third video of real analysis. Today's learning objective will be to introduce and learn about the supremum and infimum of sets. Starting off with our first definition, we have a number S is called the supremum of a set A, provided that S is an upper bound of A, and if there's another upper bound U of A, then U is greater than or equal to S. Likewise, a number I is called the infimum of a set A, provided that I is a lower bound of A, and if L is another lower bound of A, then L is less than or equal to I. A more common phrasing is that the supremum of a set is the least upper bound of that set, while the infimum is the greatest lower bound of that set. Looking at this visually, this means that if we either have a closed set from -3 to 3, or an open set from -3 to 3, the supremum and infimum will both be the same. The infimum being -3 and the supremum being 3. This is an improvement on the definition of max and mins, since they did not include elements which weren't in the set. So the open interval from -3 to 3 has no max or min, but has a supremum and an infimum. This leads us to our next note, which is that if a set has a maximum, then that maximum is the supremum. And likewise, if a set has a minimum, then that minimum will be the infimum. This is due to the fact that the max and mins are the smallest or greatest upper bounds of that set. Moving on to our first proposition, the open interval from 1 to 4 has 4 as its supremum. Now these proofs will all follow the same pattern. You have two things you need to show. One, that 4 is an upper bound, and two, that if there's any other upper bound, to show that 4 is an upper bound of the open interval from 1 to 4, we first unpack the definition of being in an open interval, which tells us that if we have some element x in the interval, then x will be strictly less than 4. And if x is strictly less than 4, then x is also less than or equal to 4. And so 4 is an upper bound by definition. To show that 4 is the least upper bound, we will do so with a contradiction. We start by assuming that u is another upper bound for the interval, but u is strictly less than 4. We then consider u plus 4 over 2, and we notice that u plus 4 over 2 will be strictly less than 4 plus 4 over 2, since u was strictly less than 4, and we know that 4 plus 4 over 2 is equal to 4. Further, we have that u plus 4 over 2 is greater than u plus u over 2, which is equal to u. So, u plus 4 over 2 is between u and 4. Since u is an upper bound of our interval, and 2 is in our interval, we have u is greater than or equal to 2 by the definition of an upper bound. Thus, we can get this chain of inequalities that says that 1 is strictly less than 2, that's less than or equal to u, that's strictly less than u plus 4 over 2, that's strictly less than 4. So, we can conclude that u plus 4 over 2 is also in our interval. But we also stated that u was strictly less than u plus 4 over 2, which contradicts our hypothesis that u is an upper bound of the interval. That new upper bound will be greater than or equal to 4, thus making 4 the supremum of the interval. Therefore, if u is an upper bound of the open interval from 1 to 4, then u is greater than or equal to 4. Thus, the open interval from 1 to 4 has 4 as its supremum. Our next proposition says that if A has supremum 5, then B, which is equal to the set of real numbers such that 2x plus 4 is in the set A, has supremum 1/2. Starting the same as before, we want to show that 1/2 is an upper bound of B. To do this, we assume some arbitrary element in B called B. Then we use the definition of being in the set B to say that 2B plus 4 is in A, by definition of B. Since 5 is the supremum of A, it is an upper bound of A, and so 2B plus 4 will be less than or equal to 5, because 2B plus 4 was in A. Thus, 2B is less than or equal to 1, and B is less than or equal to 1/2. We've shown that if B is in B, then little b is less than or equal to 1/2, so 1/2 is an upper bound of B. Next, we'll prove that if u is an upper bound for B, then u is greater than or equal to 1/2. Once more, we do this with contradiction. We assume that u is an upper bound for B, but u is strictly less than 1/2. Now we consider 2u plus 4, which we know is strictly less than 2 times 1/2 plus 4, which is equal to 5. As 5 is the supremum of A, and 2u plus 4 is strictly less than 5, we conclude that 2u plus 4 cannot be an upper bound of A. This means there exists some A in A such that 2u plus 4 is less than or equal to A. Now consider A minus 4 over 2. Since 2 times A minus 4 over 2 plus 4 is equal to A, which is in A, we know A minus 4 over 2 is in B, by definition of B. We also find that since A is in A, we have A is less than or equal to 5, because 5 is the upper bound of A. Thus, A minus 4 over 2 is in B, A minus 4 over 2 is strictly greater than U, and A minus 4 over 2 is less than or equal to 1/2. Given all these equalities, we have a contradiction between A minus 4 over 2 being in B and A minus 4 over 2 being strictly greater than U, since we assumed U was the upper bound of B. Since we've obtained a contradiction, it must be the case that U is greater than or equal to 1/2 for all upper bounds U of B. Some interesting notes that may be useful for proving in the future are the following. Moving on to our first theorem, the completeness axiom. This states that if a set of real numbers is bounded above and not empty, then it has a supremum, and if a set of real numbers is bounded below and not empty, then it has an infimum. This neatly ties together boundedness and supremums and infimums. Our next proposition states that the set of natural numbers is unbounded above. We will use the completeness axiom to prove this. We start by assuming, for the sake of contradiction, that the set of natural numbers is bounded above. Since the set of natural numbers is non-empty, the completeness axiom would tell us that the natural numbers has a supremum S. By definition, S is an upper bound of the natural numbers. And if U is another upper bound of the naturals, then U is greater than or equal to S. Thus, if we consider S minus 1 being strictly less than S, since S was the supremum, s minus 1 cannot be an upper bound of the naturals. In particular, this means that there exists an n in the naturals such that s minus 1 is strictly less than n. This implies s is strictly less than n plus 1. Notice n plus 1 is in the naturals because 1 is in the naturals, n is in the naturals, and the naturals are closed under addition. So n plus 1 must be in the naturals, and s being strictly less than n plus 1, where s was the supremum of the naturals. This is a contradiction because s was a supremum, and so it is an upper bound of n. Thus, we've reached a contradiction, and we can conclude that the naturals are unbounded above. Moving on to our second theorem, the Archimedean property, which states that if a and b are greater than 0, there exists some natural number such that n times a is strictly greater than b. To prove this, we'll assume for the sake of contradiction that there's some a and b greater than 0, for which n times a is less than or equal to b, for all n in the natural numbers. This would mean that n is less than or equal to b over a for all n, which is saying b over n is an upper bound for the naturals. This contradicts proposition 12, that the naturals are unbounded above. Proposition 13 states that if x is strictly greater than 0, then there is a natural number such that 1 over n is strictly less than x. To prove this, we use the Archimedean property with a equaling to x and b equaling to 1, which implies that 1 is strictly less than x times n, and so 1 over n is strictly less than x. Our third theorem is the density of the rationals. If a is strictly less than b, then there exists a q in the set of rationals such that q is between a and b strictly. Our final proposition states that the set of real numbers such that there exists an n in the natural numbers where x equals 1 over n has 0 as the infimum. To prove this, we'll start by showing that 0 is a lower bound. To that end, we know that since n is a natural number, n is greater than or equal to 1, which is strictly greater than 0. Thus, 1 over n is between 0 and 1. In particular, 0 is less than 1 over n, and so 0 is less than or equal to 1 over n. Thus, 0 is a lower bound. For the sake of contradiction, we'll then assume that there's another lower bound, L, such that L is greater than 0. By proposition 13, there is a natural number n such that 1 over n is less than L. This contradicts L being a lower bound. We have both conditions, that 0 is a lower bound, and that if L is another lower bound, then L is less than or equal to 0. Thus, 0 is the infimum of the set. Thank you all for watching. Have a nice day.